In this podcast, we'll be going over solutions, various concentration terms used for solutions, solubility as applied to reaction, writing, and reaction prediction. So before we talk about solutions, do you know why everyone goes to chemists with their problems? Because they have all the solutions. So what is a solution? A solution, as we had talked about in chapter 1, is a homogeneous mixture. It's a mixture that's even throughout, and it is made up of two or more components. The components in a mixture are called solute and solvent. Solute is the component that's present in lesser quantity, and solvent is the component that's present in larger quantity. There are various ways of expressing solution concentration, and they are used in different circumstances, and we'll go over each of these in detail. These concentration units for solution are molarity, molality, mass percent, mole fraction, and sometimes, very crude terms like how many teaspoons in a cup of water, or sometimes parts per million. Let's look at some of these concentration terms and when are they used. The most commonly used concentration term, and one of the more accurate ones, is molarity, which is written with uppercase M. Molarity of a solution defines how many moles of solute have been dissolved in a particular volume of the solution. So molarity is defined as moles of solute per liter of solution. Because the volume of solution is dependent upon temperature, molarity is a concentration term that changes with temperature. Hence, it is not very useful in the laboratory situations where the temperature is changing through the experiment. You would not use molarity in such cases. Molarity is used generally where you're conducting an experiment in the lab without change in temperature, such as titration. The next concentration term is called molality, and molality is defined as moles of solute that are present in 1 kilogram of solvent, not solution, but solvent. So its units are moles per kilogram, or sometimes it is just commonly referred to as molality or lowercase m instead of writing as moles per kilogram. Now if you notice, there is no volume term here. It's all about moles and mass, which stay pretty constant with temperature. So molality is a term that can be used where the temperature of experiment is changing, such as boiling point elevation, freezing point depression, etc. Even though molality and molarity sound very similar, there's a lot of difference between them. To make a molar solution takes a totally different methodology than a molal solution. So that takes us to this big question, which is more concentrated, or are they equally concentrated? 1 molar aqueous NaCl or 1 molal aqueous NaCl? I'm sure by now you've watched the links that are on the website to make standard solutions, and you know how to make a molar solution of NaCl. I would just quickly tell you to make a 1 molar NaCl, aqueous NaCl, 1 molar. What you need is 1 moles of solid NaCl, and dissolve it till the volume of solution becomes 1 liter. For this, you use a special equipment called as volumetric flask. And in this flask, you'll weigh out and put 58.5 grams of NaCl, which is equal to 1 mole of NaCl. And then you add a little bit of water to dissolve the solid, and then you make up the volume till the mark so that the solution volume is 1 liter. Please note, you do not want to add 1 liter of water to 58.5 grams of NaCl, because if you did that, then because when the solid dissolves in water, the total volume of solution will actually be greater than a liter, and it will not be 1 molar solution. However, to make a 1 molal solution, that's exactly what you do. You take a beaker, you will add 58.5 grams of NaCl to it, and now you'll add 1 liter of water to it. So will the final volume of solution be 1 liter? No, it'll be actually greater than 1 liter. Now, if you look at the methodology of preparing 1 molar versus 1 molal solution, can you answer this question? Take a moment to ponder. You may pause the podcast. The answer is 1 molar solution is more concentrated because it has lesser water than 1 liter. And remember, density of water is 1 gram per ml, so its mass and volume are equal. The next term, which is not often used, it's a rather obsolete term, but we still go over it, is called normality, written with uppercase N. Normality is molarity times acid-base equivalence. Acid-base equivalence refer to number of H plus or OH minuses that are present in acid or base, and previously normality was used to express concentration of acids and bases, but now this concentration term is not used very often. Mole fraction is generally used in terms of gases. It is little cumbersome to calculate, even though it's a pretty accurate representation. And you have to think through to understand what mole fraction is saying. It's not as simple as parts per million or mass percent, hence its limited use. Mole fraction is abbreviated by uppercase A, and mole fraction is written in terms of one of the components in mixture. So if your mixture had many components A, B, and C, what is the mole fraction of A? Mole fraction of A will be moles of A divided by total moles. And because it's a division, mole fraction is a ratio. There are no units for mole fraction. This is a practice problem, and you might want to solve this and see if you get the answer. One note, sum total of mole fractions of all the components in a mixture would always be 1. So you do get fraction for mole fraction, and generally we write it to 2 places of decimal. Mole fraction is a good unit, but not so easy to compute or to figure out by visually looking at it. It's kind of hard to figure out, so it's not that much used. A very important unit though. The next and very widely used unit is called mass percent. Mass percent is an easy way to express concentration of solution, and oftentimes in grocery stores, a lot of the solutions are the concentration of a lot of solution is expressed in mass percent. Mass percent can be written mass over mass, or mass over volume, or volume over volume. If you look at your medicine cabinet, rubbing alcohol, or if you look at vinegar in your pantry, you'll see that generally these concentrations are expressed mass over volume or volume over volume. So what are each of these? Mass percent is defined as mass of solute over mass of solution times 100. Mass percent in terms of mass over volume is mass of solute over volume of solution times 100, and mass percent in terms of volume is volume of solute over volume of solution times 100. It's very widely used, easy to compute, easy to eyeball. So few questions to ponder here. What does a 2% mass by mass aqueous NaCl mean? It means you have 2 grams of NaCl in 100 grams of aqueous NaCl solution. So how much water is present in this system? 98 grams. Very good. What does a 2% mass by volume aqueous NaCl mean? It means there is 2 grams of solid NaCl that's dissolved in 100 grams of 100 ml of solution. Not grams now, because it's mass over volume. 2% volume by volume generally would not be a term used in conjunction with a solid dissolving in a liquid, but if it were a liquid, it'll mean there is 2 mils of whichever liquid we used here dissolved in 100 mils of solution. So these are other questions to ponder. What mass percent unit are you most likely to find your vinegar's concentration expressed in? A salt solutions. Think about it, and we'll discuss it in class. And this is a practice. These are a couple of practice problems for you to deal with mass percent and mole fraction. I hope that you'll really try them, and if you have questions, you will ask me those questions in class. The next concept in this chapter is called titration. Titration is a laboratory procedure that is used to figure out the molarity of unknown acid or base by treating it or titrating it with standard acid or base. A standard solution is whose molarity is known. So if you have an acid whose molarity is unknown, you can titrate it against a base of known molarity and figure out what is acid's molarity. So how does this process work? In this process of titration, the basic concept is at equivalence point, moles of acid become equal to moles of base. What is equivalence point? It is when acid and base completely neutralize each other. And how does our eye find the equivalence point? Because we cannot really look inside the solution. So to make equivalence point visible, we use something called as indicators. Indicators are weak acid or bases themselves that change the color with change in pH. Because around equivalence point the acid or base is turning into a salt and is changing the pH of solution, the indicators are carefully chosen to change color around equivalence point. Actually, the point where indicators change color is called endpoint, and in a good titration you'd hope that endpoint and equivalence point are fairly close, negligible enough that you can almost use this point as equivalence or endpoint. So at equivalence point, moles of acid become moles of base. If you wanted to figure out moles of acid, let's say your acid was unknown, you know, if both are solutions, then moles of acid will be M1 times V1, because molarity is moles over volume. So moles are molarity times volume. And here, you know how much volume of unknown acid you took. You know the molarity of your standard solution. You know the volume of your standard solution that you had to add to get the endpoint. And using that you can calculate the molarity of unknown acid. This is the basic principle behind titration. Now what are some of the other ways you can get the moles? If you are using a solid acid, let's say your acid here that you were trying to find the identity of was solid instead of solution, then you can figure out the moles of solid acid by just taking its mass and dividing it by its molar mass. Then you know how many moles you put in the flask. Or if you had a gas, then remember you can always use Pavnert equation to get the moles of the gas. So there are three ways of getting the moles. Moles could be using M1 V1 if it is a solution, using mass over molar mass for a solid, and using Pavnert equation for a gas. I would recommend you watch this movie. It's a great movie on titration. Now titration, with the same concept, you can also, the concept used in titration M1 V1 M2 V2 can also be applied in dilution situation. We know that acids and bases are shipped to us from the companies in concentrated form, because we can dilute it easily, but to concentrate a solution is very hard. So we are shipped concentrated acid and bases, and dilution is a very common practice that a chemist or a student will do in the lab. The concept used behind dilution is the same. M1 V1 initial molarity times initial volume is equal to final molarity times final volume. The only thing you have to be careful about is in the terminology of the question. Sometimes they'll ask you how much water must be added, and at other times they'll ask you what's the final total volume of solution. Those two are different things, as you can see in this example. In this example, the total final volume is 1.25 liter, but you only need 0.75 liter of water because you had 0.5 liter of original concentrated solution. And while we are here, guys, I would like to remind you from the safety presentation, remember AAA, always add acid to water while diluting. Never add water to acid, because it's a highly exothermic reaction if you add water to acid, and the acid can jump in your face. So remember AAA while diluting acid. And these are some practice problems. I'd recommend that you please do each of these. Each of these has been carefully chosen and helps you clarify some concept. Now let's talk a little bit about the properties of solute. Remember, solution is a two-component system, And here it rushes again on me, but I'm sure it'll come back. So I'm going to keep talking. Let's continue with solutions. And solutions are two component system with solutes and solvent, and solutes have certain properties. The solutes could be ionic compounds, which we commonly call as salts in chemistry. A salt does not mean NaCl, but it means an ionic compound. Do you guys remember how we identify ionic compounds? Ionic compounds are characterized by the presence of a metal cation in them. That's an ionic compound. A molecular compound does not ionize because its intramolecular bonds are stronger. So because if you remember, molecular compounds are formed by sharing of electrons rather than transfer of electrons. So the intramolecular bonds are stronger and they don't ionize. And acids and bases ionize only if it is strong acid or strong base. Electrolyte is defined as a substance which ionizes and conducts electricity. I'm sure those of you that are athletes and into sports, you understand the importance of electrolyte balance in your body, because if your electrolyte balance is disturbed, you can get cramping. Your body requires certain ratio of sodium ion, potassium ion to carry out the sodium-potassium pump. So the electrolytes are nothing but dilute aqueous solution of some kind of salt that will give you potassium and sodium ions. Rest all is just color and marketing to get big bucks from you. A non-electrolyte is a substance which in aqueous solution does not dissociate and does not conduct electricity. Strong electrolyte is completely dissociated. A weak electrolyte only dissociates partly. Do not confuse strong and weak with dilute and concentrated. So dilute acid and concentrated acid is just how much acid is present in the solution. It's showing concentration. But a strong acid, which is dilute, will still completely ionize. A weak acid, which is concentrated, will still only partly ionize. So ionization of acid or base depend on whether they are strong or weak acids. Dilute or concentration just tell you how much acid is present in that aqueous solution or how much base is present in that aqueous solution. Dilute and concentrated are not the terms that dictate the level of dissociation. Strong and weak electrolyte is a term that will determine how much or what part of the solution will be present as dissociated ions. And these animations are great. Please pause the podcast and take a couple of minutes to go over each of these animations. And with that, we are to the last part of our PowerPoint, which talks about solubility rules, which acids dissociate, which bases dissociate. You must memorize these list of strong acids, strong bases. Beryllium and magnesium from group 2A do not dissociate. And why might that be? The reason is the size of beryllium and magnesium ions so small. Even though these bonds are highly polarized, there is still very strong forces of attraction between beryllium and hydroxide ion, too strong to let go of the hydroxide. And if beryllium or magnesium are not able to let go of the hydroxide, then it makes for weak bases. So I call these strong bases as big B bases. If you look in your periodic table, there is group 1A or 1, 2A or 2. And if you write a big B, then in the big B here, beryllium and magnesium are left out. Everything else is covered here, and hydrogen is left out here. So you have all the alkali metal hydroxide and all the alkaline earth except for beryllium and magnesium that are strong bases. And this is the list of your 7 strong acid which you must memorize. Now this is about how to write net ionic equations, and this I have covered in the first reaction prediction PowerPoint, which is titled as Reaction Prediction Basics. You can look over for how to write net ionic equation from that podcast, so I'm not going to do it over again. I would recommend, however, please go on this link and it will help you in writing net ionic equation for a double replacement reaction. And with that, I will end the podcast because I've gone over solubility rule and reaction prediction on separate podcast. Thank you for listening.